Thanks, Rooney. Can you hear me in the back? Okay, so thank you for coming in. I guess maybe a little bit early for many people. And thanks for the organizers for giving me an opportunity to speak here. So let me talk about this topic, uncertainty in deep learning. I think uncertainty is something that we all feel, right? Things are changing, lack of information. So it's a very natural feeling that, all of us have experienced. So let's start with what is science without experiments, right? So let's start with an experiment. Did anybody make sense of that? I don't think so. So let me now see whether you can make sense of this one.
The man read the newspaper at lunchtime.
Yeah, I'm sure everybody made sense of that. So let me play that first audio again. Was it better this time? So what happened? So the first what I played is an artificially degraded version. It's called a sine wave speech. And and then I played the clear speech. Then I played that first one again, right? So our brains have these amazing ability to fill in the blanks, so to say, right? So make sense of with limited information, try and perceive reality, so to say. But we may not always see reality, right? So let's do one more experiment. So you might think I'm like a satanic worshipper or something by playing this song. Nothing of that sort. But did you hear Satan 3 times in that song? Nobody heard it, or how many heard it? Can you raise your hands? Yeah, a lot of people heard it. So what was this song is actually a Stairway to Heaven by Led Zeppelin, but it was played in reverse. And with the text, your brain filled in the blanks. But so essentially, I made your brain fill in the blanks by playing the song in reverse and showing you the text, right? But it was unintended, right? I mean, there's nothing like that. But this is a serious thing. You can read this article called "Backmasking" on Wikipedia, and Led Zeppelin was accused of using backmasking to promote Satanism. I think somebody sued them in the US. So this is a real incident, right? So now, what is its relevance to our topic today? Deep neural networks inspired by the architecture of the brain. And this is a statement I took from Reddit. Jeffrey Hinton, one of the pioneers of neural networks. So he did Ask Me Anything on Reddit a few years ago. So it's important to note that these algorithms are inspired by how the brain works. Of course, we don't know. I mean, he himself says that there's a lot of credibility to the idea that we learn these layers of representations. However, we really don't know how exactly the magic in the brain works, right? But what I'm trying to say is that we know that our brain indeed is capable of, doing magic, fill in the blanks. But of course, also, we may not perceive the truth, right? So it can be manipulated to see what is not there as well. So if the neural networks were inspired by that, do they also have this property, right? Of course, we know that, like Professor Pushpak talked about some of the, great results using deep neural networks. So that is a positive side. But what about the other side, right? So just to, show for those who are not familiar with deep neural networks in pictures. So if you have these two classes, like this is called this half moons data set, you have these red and blue dots. and you want to build a classifier to separate them, right? So a neural network can learn this. And why is this something that cannot be learned with simpler models? Because they cannot be separated by drawing a line. So you need a non-linear decision boundary, and with nothing but giving these points, a neural network is able to figure out and separate them, right? So it's a, it's a great as a machine learning model. Now let's look at one more data point before we kind of get into the talk. So what you're going to see here is a neural network trained to detect stop signs. So you're all heard about self-driving cars. So this neural network is trained to detect a stop sign. Let's see what happens. So did you notice the stop sign on the left has some stickers on it, but the neural network thinks it is a speed limit 45 sign. Whereas on the right, it is fine, it's a stop sign. So this is from a recent paper in, and there have been many such, manipulations, reported in literature. This is a paper from in 2018 from Computer Vision and Pattern Recognition Conference. So what goes wrong here? I mean, if I can put a sticker on a stop sign and get your car, to drive through the stop sign, what happens, right? So that's not a good sign. So what is the issue here? So as we said earlier, neural networks are very powerful function approximators, and they compute these point estimates. For example, the probability that a given sign is a stop sign. But they can make overly confident and incorrect predictions as well. So we will look at one sub problem in that category, and what we are going to look at is let's train a neural network, give it what is called as in distribution data. That is data that is similar to what we trained it with, but we will also test it with out of distribution data. That is data that it was not trained with, in order to see what happens. Because the stop sign thing is a little bit different example where it is more or less in distribution, but some manipulation of that sign leads the neural network to think that it is a 45-mile-per-hour sign, right? So there are many similar problems, adversarial and so on, like how do you trick a neural network, how do you fool a neural network? But we are just going to focus on this in distribution versus out of distribution data. And from an industry standpoint, nobody gives you ready-made data sets. You have to explore the data on your own, and you have to understand, for example, what kind of additional data to collect and so on. That is where the application of some of these techniques are, in order to understand your in-distribution data, what can reduce uncertainty, and also how do you prevent your models. For example, you're building a speech model. People can say anything into that. How do you control that, right? You can't really, in traditional programming, you can say if bad input, maybe throw an error. But how do you do that in neural networks, right? So this is the example I'm talking about. So if you're writing a traditional, let's say, square root function, you can put an assert statement saying that, the input must be greater than or equal to 0. But how do you do that in the case of neural networks? Because this stage happens before you have even recognized that it is a stop sign or it's a 45 miles per hour sign, right? So you can't handle it through a traditional programming approach. So you need to, before because the sign is perceived, right? Here the sign is perceived incorrectly. And what we are going to look at is even the probability estimates may not be accurate. So in such a case, how do you explore the data? How do you understand the problem? That is what we are going to focus on. So if you look at a deep learning neural network, of course, a neural network can have many, many layers. That is why it is called deep. I'm just showing you an example here where, let's say there is an input layer, there is one hidden layer, and then there is an output layer. And when we train this neural network, this is what we learn, these weights, W1, W2, W3. So if you look at the neural network in the weight space, it is a point in that weight space, right? Given this configuration, it's a point in that weight space. So it looks very certain about what it learned. Don't we all have doubts? So how do we now enrich this model with a neural network that is capable of having doubts? So the idea we are following is from a paper by authors at Google DeepMind. It's called Weight Uncertainty in Neural Networks. So instead of having these single real numbers as weights, the idea is to represent them as probability distributions. And then, in the paper, they show how those probability distributions can be learned from the data. So our thinking is that for a given input, once you learn these distributions, we can sample from those distributions, and then we can generate the predictions, and then we can assess the uncertainty in the predictions. How do you assess the uncertainty in a prediction? You have given a probability distribution. You can compute what is called as entropy. It's a measure of uncertainty. Okay, so this is the idea. On the left side, you have a standard deep learning neural network with those weights learned as real numbers. And on the right side, we have this new architecture where the weights are actually probability distributions and not single numbers. And how do we go about this? So if we have those distributions, we can sample the weights. As we run a prediction, for example, pass an image through the network, we can get it to predict. But in that prediction, we will use samples from these learned weight distributions. And let's say if we do this 10 times for the same input, for input I, I'm doing this 10 times, I will get different probabilities, right? So now I can actually compute I can average these, and I can compute the entropy. So first, definition of entropy. So let's take a simple example. If you have two classes, with your classifier outputs a probability of 0.5 for both, you know that is where the highest uncertainty is, right? The classifier has no clue what it is. It's saying it could be this or that with equal probability. Whereas if it is 1, 0, then you know that entropy is 0 because there is no uncertainty. And somewhere in the middle, right? I'm 90% sure that it is class 2. In that case, the entropy works out to 0.47. So this is the basic approach that we run the input through the neural network, a certain number of times, compute the probabilities, average them, and then compute the entropy. Okay. And how are these different runs different? Because we are sampling the weights from the learned distributions. So there is a long history of this approach in neural networks. It started in the 80s by some of the pioneers, David McKay and others, and it's called the Bayesian inference on neural networks. So what is the idea? The idea is to learn these weights from the data, where W is the weights and D is the data. So the first formula is Bayes' theorem, right? And how do we predict? For a given new input X star, we compute the prediction as an expectation, as an averaging over the probabilities, right, sampled from these weight distributions. So this is in theory. The problem is this, doing this in practice is quite hard, because if you notice this, what is called as evidence, the denominator in that Bayes formula, probability of data, so that involves, a simple way to understand this is, if you have 10 weights, then there are and assume that they're binary, there are like 1024, 2 to the power of 10 combinations, right? So in today's neural networks, you have millions of weights. So it's simply impossible in terms of the number of configurations possible. So this kind of computing that exactly is intractable. So that is where the approach, which is becoming more popular these days, this is called, how do you compute an approximation? So we said that we can't compute the exact distribution on the weights. So we are going to compute this variational, called as a variational approximation. So the idea is simple, that if you can't compute it exactly, let's choose a family of distributions. For example, I choose Gaussian. And then we can compute the parameters that minimize divergence with the true distribution. Okay. So I'll explain that what we mean. For example, what is the parameters of the Gaussian family? Let's say mean and standard deviation. And we want to learn that from the data such that the divergence is minimized. Okay, so what is divergence? So this is what so as we said, we want to learn that first distribution, but we can't compute it exactly. So we are going to use a distribution Q, which is an approximate distribution, and it has parameters like mean and sigma for Gaussian. And what is divergence? Divergence is the additional uncertainty that we introduce into the predictions if we use probabilities from one distribution to predict events from another distribution. Okay? And we are trying to minimize this. So we have a true distribution. By using an approximate distribution, we will introduce additional uncertainty, but we want to minimize that. So that is a problem. Okay, one more issue is there, if you notice, but the true distribution we don't know. If we knew that in the first place, then we don't need to do all this thing, right? So how do we overcome that? So just an illustration of divergence, or also called as KL or Kullback-Leibler, for the people who came up with this idea. So suppose you have a distribution P with the two probabilities, 0.8 and 0.2, and now you're going to learn this Q, right? So you can vary, let's say the first value of Q, because other value will be 1 minus whatever that value. So let's say we parameterize as theta is the first value of Q, first probability of Q, then the other is 1 minus theta, right? So we can vary theta. As we vary theta, we can see where the divergence is minimized. So we can turn this whole thing into an optimization problem, provided we knew the true distribution. But we don't know the true distribution, so how do we overcome that? So again, one more picture to kind of give you a more intuition. So this is that the true distribution is that orange one. We can't compute it directly. So we want to slide this Gaussian with the mean and variance, and we try and minimize the divergence. Okay? So this is the idea of variational approximation. Okay, so now how do we overcome this challenge of not knowing the true distribution? This is where I think I'm not going to go into the full math, but the basic idea is this, that you can decompose this into two parts. One is that divergence we talked about, and the other is what is called as a evidence lower bound. So the idea is that because we don't know the exact distribution, we have an approximate one, and we know that the scale divergence is actually a positive quantity. And our objective is to minimize that positive quantity, right? So the equivalent thing is we can maximize that what is called as the evidence lower bound. So we turn the problem into, instead of minimizing divergence, we can maximize the evidence lower bound, and that is tractable. Okay? So this is the basic idea behind variational approximation. And as you know, all the what is today called as probabilistic programming languages. You may have heard about Pyro, which is from Uber, is built on top of PyTorch from Facebook. Or there's this another one called Edward, which is merged with TensorFlow, or PyMC3. So these are all called probabilistic programming languages. They all support this variational inference today. So you can actually use these techniques in the models that you're creating. So this is very much available as part of all these open source packages. Okay, so now let's discuss some experiments. By doing this, we built a model which I said is a Bayesian neural network with weights as distributions, and we are now trying to understand the uncertainty in the data, right? By looking at two data sets. One is what is called as a fashion MNIST. So I'll show you the images. Nothing but a whole bunch of 10 classes of fashion like shirt and so on. And the another one is out of distribution data, which is called extended MNIST, which is images rotated and things like that, right? So we are going to train a neural network, a Bayesian neural network on the fashion MNIST data. We are going to look at as I explained, trying to compute the entropy and see what its usefulness. And you're also going to feed the same network data from out of distribution. So the network was never trained for this extended MNIST. We're going to see what happens. So this is the fashion MNIST data. So there are 10 classes. So this is a sample of images like t-shirt, dress, bag, and so on. Right? So when we compute these predictions, as you see, the x-axis is the maximum predicted probability, right? And the color indicates whether the prediction was correct or not. And the y-axis is actually the entropy. Okay, so remember our picture that we are going to run images through this many times. We are sampling weights. Therefore, we have two measures to assess. We get the probability as before, but we also can compute the entropy of the prediction, right? So one thing you see is that even with, let's say, some of this towards the right top, as you see, the probability could be quite high. You know, it's like the network is 0.8. With 0.8 probability, it is certain about some things. But as we know from the labels, it is an incorrect prediction. And as you see, the entropy is also quite high in some of those cases, right? Of course, the left side, is more understandable because the probability is low, entropy is quite high as well there. So in this case, the network is not at all confident about these areas. But even where the network is confident, like let's say 0.7 probability, as you see the entropy rising, those are candidates to be examined further, right? Because you know that you can't rely only on the point estimate of the probability alone. So which are those, for example, where the probability of the prediction is 0.8 or more, but which are the cases where there's high entropy? So we took a sample of those images. So as you see, the network is, the probability of prediction is quite high, but the entropy is high because they look very similar. They are either a shirt and a top, which may not be easily distinguishable even for a naked eye without actually looking at it closely, right? So they are very similar images, and we can see this more clearly. So this is actually the the points from the test set with the actual labels, these clusters, and you can see what they are. For example, a trouser, there's no confusion. More or less, everything is correct. Whereas here, if you see, there's a lot of, and what are these circles? These circles are the top 50 high entropy images are circled, right? So as you see, where is the highest uncertainty? It's actually between the red and the blue classes, which is a dress and a t-shirt or a top, right? So this is the area where there is highest uncertainty. And for in-distribution data, by doing this and by understanding this, we can decide what are the next steps to take, right? Should we collapse the classes? Should we get more images or more training data to, or should we do more feature engineering? What else can we do, right? How do we improve the boundary between these classes, right? So what is the right action to take to address this issue, right? So that is the utility or practical utility of doing this, to understand and explore your data better. How do you improve the accuracy further, or what else can you do, right? So that helps in arriving at the right decisions based on this kind of analysis. So now let's look at the out of distribution data set. So as you see, there are these are kind of images. It has nothing to do with clothes or nothing to do with fashion, right? But you'll be surprised to see, the network is predicting with very high probability, even things that are clearly nothing to do with fashion, right? So this is this is similar to our stop sign example, although not exactly the same, but it's a similar kind of a thing that's happening. As you see, the entropy is quite higher, but here again, looking at not just the probability, but trying and assessing the entropy can help in identifying that these could be treated, or these should be treated with caution, right? So this is the other application of dealing with out of distribution data. Okay. So as we said, if people, going back to our earlier example, if people claim that Led Zeppelin was trying to promote Satanism, then somebody had to critically evaluate it, right? So just like that, if neural networks are inspired by the brain, how do we critically evaluate its predictions? How do we know whether it really knows what it claims to know, right? So that is an important problem. So just to summarize, we had two data sets. In distribution is the fashion data set, and out of distribution is the digits data set. We trained the Bayesian neural network. So remember, the weights were not point real numbers, but they were distributions. And then we could use entropy as well as this KL divergence. We could compute or learn those weight distributions. We could sample the weights. We could run the network through. I mean, we could essentially, it's like you're guessing something, and if I ask you that 2 or 3 or 4 different ways, you might give me different answers, and then I know that you probably are not really sure what what you're thinking about, right? So this is one way to evaluate whether I really know whether you really know what you claim to know, right? So a similar process in the case of deep neural networks, and it can be useful to explore your data. There is this area called active learning, which is basically, how do I collect additional samples? What kind of additional data can I collect to improve your, your training or your testing accuracy, right? And how can you prevent, or how can you even know whether somebody is passing through your neural network out of distribution data and fooling it? So this is a kind of analysis that can help at least address some of these issues. So thank you, and any questions?
Hey, I'm Tejas. I'm a data scientist at Nodal AI. So I had a question. We are actually doing something similar to this, and when you say you don't calculate point estimates for weights and you draw probability distribution, there is a difficulty for back propagation because you're not certain that like you're just sampling out of the mean and standard deviation, right? So we use something called the reparameterization trick. Do you know, or what do you use for like basic neural network?
So the the paper actually goes through the details. So yes, it's a reparameterization trick to to learn. So essentially, they are trying to maximize the elbow. So that is done through gradient descent only, right? So essentially, the algorithm given in the paper is compatible with backpropagation. So it is with minor changes in your code, you can actually implement this variational inference using a framework like PyTorch. In this case, I'm using PyTorch, and then you can compute these weight distributions.
Okay, cool.
Hi. Just want to know what are your comments on the graph that you showed for out of distribution data for those points that had high probability but low entropy. So, for instance, what would I do with those points, or what observations can I draw from those?
Yeah,
points?
so this is an active area of research as to how do you really see so like we said, we are learning different layers of representations, right? So after all, some of those features in your out of distribution data could be shared within your in distribution data, at least at the lower layers. So it's not completely, so in that sense, how, people have shown that even sometimes even changing one pixel can dramatically alter the what the network thinks what the image is. So this is still not a solved problem. What we are showing here is that many of the cases, I agree with the because towards the right corner, probably that's what you're talking about, right? This right corner. So probably, like example, the right bottom is an area where you still have a problem. Yes. Yeah, but this is an active area of research, and by no means it's a solved problem in that sense.
So what you're essentially saying in this slide is that because it is out of distribution, there is a larger proportion of higher entropy in cases of even high probability. Is that what the conclusion is?
Yeah, so what I'm saying is that even in the case of 0.8, for example, you can use a simple entropy threshold, right? So in that case, if you compare this with the previous one, see, if you look at the entropy scale, if you'll see that in this case, the entropy is much higher. So you can use that as another data point to evaluate whether this is really out of distribution or not. So it's one indicator to use in this case. Does that answer your question? Yes. Yeah. Yeah. So basically, even if it's high probability, you look at the entropy axis and say, and you cut off, right? At some point, if you draw a line, you can catch a lot of outer distribution data through that simple mechanism.
Yeah, hello. Hello. So I'm Rahul from Walmart Labs. So I was wondering, so I myself have used Bayesian.
I'm not able to hear you.
Okay, can I get another mic? So am I audible now? Hello, hello.
Yeah, maybe a little more louder. Yeah.
Okay. So I'm Rahul from Walmart Labs. So I was wondering, so how scalable are these Bayesian neural networks? Because I had used it a couple of years back, and that time it really wasn't scalable. So what's the current state now?
Yeah, so I would say that is a challenge in terms of not to very large data sets, but they are, medium level networks are fine. At least, that is, I don't think that is an issue. But you're right in that very large data sets, it could be an issue. But again, you can work with, a smaller sample of data and see, right? In this case, like you're using it as a data exploration device, you can take a decent enough sample and see whether you can learn the weights and then explore the data.
So you use something like this for initialization of the weights for the larger network?
That could also be you can use that as initializing criteria for the larger network as well. So there are many applications around this in terms of active learning is one. Using these learned posteriors, you can initialize, like you said, it could be used for multi-M bandits exploration and so on. So the learned weights itself could be useful as as a next step to, or a processor initialize a larger this thing. But it could be a data exploration device as well with a sample of your data, not your entire training data set. Because here your focus is not on beating the benchmark, right? Your focus is more on trying to understand the uncertainty in the data and seeing what kind of, it's more of a data exploration device. At least that's the way I'm using it.
Yeah, so mostly taking a corrective action on whatever things are needed. But are there any references, recent references on the papers on where they have used Bayesian neural networks for large scale data kind of thing? Since you are active in this area, so I wanted to know.
Are there any recent references?
Yeah.
Yeah, so there are a lot of follow-up work on this, on variation inference and, and solving this out of distribution thing. If you want, we can talk that out offline. Yeah.
Hello. Any more questions? We have another good 5 minutes to go, so we still have time for discussions. Questions?
Hi, I'm Arun from Evive Labs. Just a simple question. This work, how do you actually use it in your company?
One of the areas we are using it is for, active learning, trying to understand the data and see how we can improve, classification accuracy. What other things could be, what other kind of data, because as you know, data tagging is quite expensive. So you don't want to tag, just keep tagging data in the hope of improving classification accuracy, right? So if you can get the data where the value of that data is more, and then, so there is a justification to that tagging effort. So that's one way we are looking at it.